Hi, good afternoon everyone. Hi, good afternoon everyone once again. And in the next half an hour, we'll be talking about why database matters in the current product access space. And we'll be sharing like some of the experiences that we had while working and implementing this particular use case. And start. So as an introduction, I'm Dheeraj Mudgil, and I'm Enterprise Solutions Architect, and I've been working with the Barclays for the last 13 years. And I'm the architecture owner of the fraud platform, defining the strategy. And have been worked in various domains like payments, fraud, cards. And for the people who do not know Barclays, it's some of the facts basically is lesser known is it's older than UK. It's 29 years old. Right, and it has been offering a lot of financial products, and it has been an innovator in the financial market. Let's say for the ATM that was introduced by Barclays first in the UK. Similarly for the cards, Barclays was the first one to launch that. And there are some innovations that are happening, and if you're interested, there's a link out there you can check out. So starting with the question, how much data we generate today? So we currently in 2019 touched 5 billion mobile internet users. Our internet users basically increased by 83% in the last 5 years alone. So we see the trend is increasing. Also by 2023, 463 exabytes of data we will be generating every single day. So whatever data we are generating, somewhere someone needs to consume it. Even if you want to ignore it, some of the companies, they still have to filter it out. So there will be a lot of processing power that will be required. So all of these are happening because of the changing landscapes and behaviors, which we'll talk about, right? And then we'll get into the actual fraud use case. So some of the drivers are there, like IoT, mobile, sensors, smart TV, and you name it. Now trends in general. So we see that the devices we are carrying, whether it is wearable, whether it is number of phones, or whether it is a number of chips within a phone, right? All that is on rise. And the new channels are opening up for allowing the consumers to make their choices or to transact. Similarly, the social media and information sharing is on the rise. There's lots and lots of social media companies, right? A lot of collaboration is increasing, and people are increasingly sharing their information, right? To some extent that they do not realize, they are sharing their privacy information as well. So. Also from an automation perspective, this is one of the key things that is happening or caught up in the last, let's say, 5-6 years, and it is on the rise about automation. All the companies want to do automation for various different reasons and drivers, and there is a desire to release the products faster in the market. Now all these different trends basically indicates that the software is going to be more complex, and whenever we talk about software complexity, inherently we talk about the vulnerabilities that it can create. Right. Now, these were the trends from the industry perspective. Talking about the customer, so the customer patience is on decline. They want everything instant. They press the button and they want information. They want the results, and also on demand. So they were happy waiting for a couple of seconds, minutes, let's say, last decade, but their patience because of the mobile technology is going down. Also the expectations that they have in terms of the provider will protect them from the fraud losses, or provider will make their life easier. So that kind of experience is, customer experience is on the rise. Also the loyalty of the product consumers towards the product, that is on decrease because there are so many options available to them. They can switch, and that is for good as well. The governance and the regulators basically are forcing so many different companies, so many different sectors, right? To provide choices and allowing the consumer to switch seamlessly. Now, all that is indicating that the customer needs are getting more complex, right? And also their behaviors are getting more complex. They would want to transact on various different channels, but want the information or the output of that transaction immediately. Looking at the fraud and fraudsters lens, and combining what we have seen in the last two slides, we have seen the barriers to compute, which is high performance compute, is and the cloud is the enabler there. So whoever is the fraudsters, they are getting more organized, and also they have access to huge amount of computing power on demand. They don't need a lot of investments. They don't need to set up any kind of data centers. Now also because the people are sharing lots of private information, personal information, the barriers to collection of the information is also going down. They can profile different sets of consumers, customers, merchants, right? I mean, then they can extract information and then they can use it to cheat or benefit or and to do kind of any proprietary exercise. Also, the sophistication of the fraud techniques, and there is a fraud supply chain. They are getting more organized. So there are tools out there. I mean, some people develop the tool, some other people distribute that tool. So their entire fraud chain, right, is working in harmony, and they are getting more organized. So these also tells us that the subtlety of the fraud, right, and the complexity of the fraudster behavior is on the rise. So if you combine what else is happening in the market and how the fraudsters will be exploring or exploiting the vulnerabilities created within the software unknowingly, so that will lead to the increase in the fraud trends. Now let's see a typical card payment journey. So we have a consumer and we have a card issuer. The consumer basically wants to shop something online, and then the card is issued by the card issuer to the consumer. Consumer now wants to shop. He logs on to one of the merchant site, and then he says, okay, I'm happy with my basket and everything, and he submits the transaction. So he wants to make a payment. The moment he presses the button, the timer starts. His expectation, as we have seen, is going down. He wants things instantly. Now let's see what the journey is, where the transaction goes. The transaction from the merchant system goes to the payment gateway. The payment gateway does its processing and passes the information out to the payment acquirer. The payment acquirer does its due diligence and processing, and then it sends the information out to card schemes like Visa, MasterCard, Diners, JCB, Credit Union Pay, whatever. So they identify who is the card issuer, and then they divert the transaction to the card issuer. So card issuer basically does its own processing, as well as then some kind of fraud detection needs to take place. So if you see, the fraud detection is happening from a card issuer perspective towards the end of the chain, right? So the fraud detection has a limited time budget, and you remember that the timer is ticking. The customer is waiting at the other end to get the transaction authorized, and there is a long chain, network hops, lot of processing, so many different parties involved, and the time needs to be shrunk down in terms of the fraud detection. If the fraud detection is not taking place within the set time budget, the timers on the upstream applications will start to go down, and you have to either bear the losses, or you have to say we have declined the transactions. That will inconvenience the customer, and the customer will stop using your card. Right? So in this case, we'll talk about the role of the jitter as well when we'll get to the next slides. Now let's get into the details of this use case. So from a consumer perspective, the consumer wants a swift checkout and a fraud protection. He wants that whatever I do, my provider is going to protect me, right? Merchant wants fast approvals and zero declines, because there is a decline, the customer will leave the shopping, right? And then he will do something else. So the merchant wants that every time a consumer tries to buy things, he gets the approval. That's his motive. Issuer wants more and more usage of the card. He wants to encourage the card usage, and the moment he says I'm declining the transaction, there's a risk that the customer will stop using the card, right? So there are some complex, and obviously he doesn't want to incur the fraud losses as well. There are complex equation here, and the challenge is from a false negative perspective, which is around the issuer protecting the fraud, right? So identifying the genuine fraud is called false negative. He doesn't want to let the fraudulent transactions go. So for that, if he puts in too high a threshold, too complex rules, right, it is going to inconvenience the customer. So that means the false positive will go high. So if the genuine customer is doing the transaction and his transactions are declined, maybe he is getting a deal, right? Maybe half price deal. He did the transaction on an auction and the card was declined. He will not be happy, right? So getting the balance right between the false negative and false positive is very, very tricky. Now, if you try to reduce the angle of these triangle, right, from a false positive and false negative, you need to be able to do lots and lots of complexity. and potentially your latency would increase because you are doing a lot of computations during the set budget. Also, it may impact your operation. So, if you see, like, I mean, the triangle is extremely complex. Not only that, you have to balance whatever you do here with respect to the total cost of ownership of the fraud platform. Now, you also need to think about the time to market, because if you continuously, like, I mean, you keep refining your rules, keep refining your engineering efforts, right, it's going to take a long time, and then you will miss out on the boat. So the build cost as well as on the operational cost. So you need to find the right balance, right, I mean, in these two different triangles. Now the key characteristics of this use case we have seen is it's a latency sensitive use case. It requires complex processing rules, and it would involve large data sets. That depends on the number of consumers who you are protecting. Okay. Also, because we are talking about the set time budget, so the predictability of the response times, right, I mean, at each layer is extremely important. Now let's see how we're going to solve this. It's very simple. All you need is build an application that contains the logic, some fraud rules, and you need to have a database where you store profiles about the customer, their statistics, indicators, and whatnot. And then you say, yeah, I have the logic, expose it via an API, and let the consuming applications consume it. And then we say whether the transaction is fraudulent or not. And the question is, which database? So there is a huge amount of technologies out there, right? I mean, so finding which one is good for your use case is not an easy choice. So there are different ways you can select. One, different people could say that, okay, yeah, I'm familiar with their particular database, let's use it. Some would say, yeah, we already have something in our technology landscape, we can use that. Also, we can pick a generic database, pick any, and then we'll make it work. We have lots of good engineers. Or we may look at the industry reports and say, yeah, this particular industry report says this particular database is good, so let's pick that up. Also, there may be some enterprise constraints, specifically in the large organizations, where they say, for this type of technology, we will not allow more than 1 or 2 databases because that's proliferation of technology, and we need to contain it from a governance perspective, right? So you can that could be one of the constraints. Also, from an MVP perspective, when you are building this, they say, okay, let's not worry about the performance right now. Let's build this functionally, and then we'll worry about the performance later. Well, you can toss a coin as well, I mean, if you wish. So, now, from a simple architecture perspective, I have kept it extremely simple. Let's say we have a client which has a need for a fraud. So it has a payload, and it needs to say, I want a fraud detection system to give me a result on this, whether this particular payload is fraudulent or not. What do I do with this? And give a recommendation from a fraud perspective. We have application logic, and we have a database which has some physical disk. So that's a traditional database DBMS architecture. And another one, like, I mean, is a shared nothing architecture which has multiple disks, different nodes they don't share any data or content. Now, let's say you picked up any of these and then we hit the performance problems. So how can we address the performance problems if we have taken an MVP approach or a generic approach? So we can scale the database vertically. If we hit performance issues, we can start caching the data in the database, caching some tables which are highly reusable tables, or even cache the data within the application itself. There are lots of technologies that allow that. But each one of them has their own constraints. Right? I mean, if you cache the data in the application, it's going to make your application complex. You need to be able to work out, like, I mean, at what point in time the cache needs to be evicted, how to ensure that the cache contains the precise data, and the RAM that the machine in which your application is running, right? What kind of RAM does it have, and how much data you are caching, right? I mean, if you have multiple applications, how are you going to handle that? So obviously, like, I mean, it will provide you some benefits, but it comes up with some kind of limitations as well. Also, like, we can go in for database clustering as another option, or in combination with the other ones. So in terms of caches, like, I mean, if you see that my RAM on each machine is, let's say, 120 GB or 400 GB, but my database is a terabyte database, or that particular table, obviously, like, I need to go for a distributed cache there. So this is cache aside, where the application needs to be modified, and every time it makes a call to the database, it also makes an entry into the distributed cache. So your application becomes more complex. It has to handle more concerns. Now, if you say I want my application to simply talk to one endpoint, not to a database and to a distributed cache. I simply would want my application to talk to a distributed cache and let the cache manage the database. That is one option that is out there. Some technologies do allow it, but even in this case, there are some pros and cons, and there are a lot of varieties of this exist distributed cache on the cache tree. Continuing with the patterns that. Same as caches, there is an in-memory database. So the difference between the in-memory database and the caches is database technology, in-memory database technology allows you to have more functionally rich items. Basically, you can do a lot more than cache. So this is in-memory database through. Another one is you can have in-memory database with persistence. So here, if you see the differences, on the left ones, there are two technologies. One is a database, another is a cache or an in-memory database on top of it. And this one basically is the memory which has been extended to persist the data as well. Continuing with the patterns, there are a few more. Now this is a lot more complex, where you have multiple different applications, multiple different databases, right? And then you can create a memory grid. But again, creating the grid comes up with lots of pros and cons. It makes your lot of applications highly performant. However, there is a cost, time, and the engineering effort that goes in. On the data co-location, some databases allows you to have your data sets which are inherently close together but are stored in separate tables, right? To be stored into the same node, so that you don't have to go for different hops. So that is some technologies allows this pattern, data co-location. Some other technologies allows compute co-location, where you are able to put your data where your compute is, right? And there are some other patterns this is a very complex pattern, and but it does provide some good benefits in case your use case can benefit from it. Yet another one is hybrid memory, where you have your indexes in the RAM and your data on the disk. Now comparing this pattern with the other ones, in-memory database patterns. So in-memory database would require your indexes as well as your entire data sets within the memory. Now in that case, if you have terabytes of data, all your let's say few terabytes, 5, 10, 20 terabytes, if the data that you are handling is small, that is okay. But if the data that you are handling is large, then the cost of maintaining that cluster becomes very high. The number of nodes in which you need to manage, right, will be higher. Let's say if your AWS nodes, or if your node has 500 GB of RAM and you have to cache 10 terabytes of data, you can imagine, and you need to make 2 copies of it from an availability perspective. So you can imagine the size of RAM footprint that you need to have, right? So that's where this hybrid memory comes into the picture, where you are storing the indexes in the RAM, so you have a lesser footprint on the RAM, and you store your data in the flash disk. That's hybrid. Now let's talk about the complexity of the financial fraud. We have just seen one use case. Now from a financial crime perspective, there are lots of complexities, like first party fraud, third party fraud, second party fraud, mules account, scams, and we have only seen a card fraud right now in our use case. Now let's say if you were to extend our architecture and our solution to address some other types of frauds. Now let's see what it may do in terms of the complexity, in terms of our database choices, or the technology choices, or the architecture choices, right? Whatever we have chosen, right, will it fit our future? Will it be extensible? How much engineering effort it would need to go, we need to put in to make that extensible. So let's say we have regulatory requirements which are increasingly going high up. We have strong customer authentication from PSD2. They are also enforcing let's say PRA, which is good for the industry because it's going to reduce the fraud. But nonetheless, they need handling. So payment validations, contingency reimbursement model, which is about protecting the customers from the scams, and the impact on this use case on the architecture as well as on the database technology. So not only we have to look at the current use case, but also how we would like to extend it, and whatever technology we are choosing, will they set us for success for our extension or not? Now in summary, seeing that the database matters in the fraud use case, if you were to look into an MVP perspective, yeah, the choices may be different, but how do you want to extend it? So each database technology comes up with its pros and cons. Functionally similar use cases may only be functionally similar, but the non-functionals basically would force you to think differently. And there is no silver bullet in selecting the database. 80% of the database use cases, basically you can easily find a good database, but the remaining 10 to 20% databases or the use cases will force you to think differently. So what may work with the deep understanding of a use case and the understanding of the data itself. Now what we use in our fraud use cases, so we went in for the Aerospike, which is a hybrid memory architecture where we are storing the indexes in the RAM and the data onto the disk. What we liked about this was the performance. It gave quick access to the large data sets and one hop to the data from the client. We didn't have to manage the cache, because the moment you talk about cache, you have to manage the database infrastructure as well as the cache infrastructure. But if you get the speed of the cache, right, I mean from a specific architecture, then you have less infrastructure to manage. So, and you don't have the cache misses. The key thing about the cache misses is if you are doing a transaction fraud detection at a low latency, let's say a few hundred milliseconds, then if you need to reach out to your cache, the data is not in your cache, you need to reach out to your database, then the transaction almost certainly will go into a STIP, which is like timers at the upstream system will go off. It provides us predictability as well as the simple architecture that we aspire for our solution to be. And it does supported our scaling needs and strong consistency and security requirements. What it is not is a relational database. It does not support SQL. And it has a bit of a learning curve. That's we have to learn it, right? I mean, we need to put the people through the training. And it's not a general purpose database, because our use case was like, I mean, in the extreme 10 to 20% use cases. So, I mean, that's why, like, I mean, we have to look for some other non-general technology. Now, some of the lessons that we have learned over time is, for this particular use case, it was very hard to choose, and some of the aspects that are frequently misunderstood or people take them very lightly, right? I mean, is around the scale and throughput. People simply think that, you know, it's MVP, let's build it functionally. Project managers, right? I mean, all the executives, they want things done faster, inherent desire, time to market. Everybody understands the constraint, but in that constraint, like, I mean, the intent of the scale and throughput and the sensitivity towards the latency is misunderstood or taken lightly. Jitter is extremely important. Now, if you see, like, I mean, if you are having database calls and you do not know how long, and you have a set time budget of, let's say, 100 milliseconds to do the fraud detection. Within that, you need to make lots of database calls, pull the data from multiple different tables, and then transform the data so that your rules engine can accept it, and then does its computing. If within that 100 milliseconds, if you say 50 milliseconds or 40 milliseconds, basically were taken away just by the database calls, right? I mean, it is 40% of your budget, fraud detection budget is taken away from you, right? So the jitter is very important. It has to provide a consistent response times, no matter what database calls you are making. Some other key ones basically are the pedigree. Now, this was another interesting point where once you have nailed down your choices to, let's say, 1, 2 or 3 technologies, right? I mean, and all of them are providing very similar features, very similar total cost of operations or ownership. How do you determine? So the way we went for this was, we started looking for the one single thing that a product specifically was originally designed for. All the products evolve, but looking into the pedigree of it, why that product was incepted, what specific problem it was incepted to solve. So that really helped us. Also, the Jepsen report, because we were looking for the consistency, so this is a brilliant resource, like Aman Baikal, so look for it. And if you have time, so try to draw some comparables from the industry in terms of references. Some more around the operational costs, and the key thing I will call out is the patching strategy. So patching strategy is something that you need to be extremely careful about, because your enterprise would have a patching strategy for the Linux boxes. Now, whether they go in for how do they go in for? Do they create a new instance altogether all the time, right? Or how do they patch? How frequently do they patch? If you have terabytes and terabytes of data, right? I mean, how long does it take for the machine to boot up? So these were the few critical lessons that we have learned, and would like to share. If you have time, right? I mean, do some POCs and get your people through some training. And of course, things change. A lot of new technologies comes in, so be aware of the vendor lock-in. So that's it. Very quick presentation.